This video is to address week number 7, task number 3. In task number 3, it asks us to first draw the line that contains the points 110 and 410. And before we go to any other part of this task, I want to first address that. So the z-value in both of these points is 0, so therefore it's actually a 2-space line, but you can represent it in 2-space or in 3-space. So what I want to show is just first and foremost the actual line. So this is the line in 2-space. Notice that A is at 1, 1 and B is at 4, 1. That's obviously just dropping the z-value off completely and putting it into 2-space. We can do that because the z is 0. And then over here in 3-space, we are now seeing that it's graphed on the XYZ plane, but notice that there is no z-value, so it has no above sea level, below sea level quality to the graph. It literally is lying on the Cartesian plane part of the XYZ plane. So I thought that that was interesting. What that means essentially is that we can actually use the 2-space idea of slope here in order to find the slope of AB. That is going to come in the second half of the problem. After graphing the line with the 2 points, it wants to describe the pair of planes that passes through that line, that provides that line as the intersection. So I actually have 2 cases here. The first case is this one, where it is the XY plane intersecting with the y=1 plane. And so I'm going to show these just one at a time. So here's the XY plane, and that is obviously the Cartesian plane where our line is resting. And then the points both have a y value of 1, so that would be the plane formation of the y=1 plane. And there you can clearly see the intersection. As we rotate it, you can see it from all different perspectives. The line is clearly passing through these 2 planes and intersecting them. We should remember that the definition of a plane intersection is always a line. So with the 2 planes. So that is the plane example that I first came up with. But then I started thinking, couldn't I have this occur through that line with multiple sets of planes? So I'm sure that this will work with many others, but I wanted to just try this out randomly. So here's another case. So what we are seeing here is, in order to create these 2 planes intersecting on the line, what I decided to do was, I know that by the definition of planes, it means that any 3 non-collinear points form a plane. So what I decided to do was use the given AB points, which I'm calling AB as the 2 points that were given in the problem, 110 and 410, respectively. So what I did here was, because the definition of plane is the 3 non-collinear points, I just randomly chose a point off of the line AB in 2 different directions. So I chose point C, and I'm going to actually get rid of these planes right now so you can see them. I chose point C and then I chose point D. And what I did after that is I used the GeoGebra option of creating a plane through 3 points. And so I went ahead and I created those 2 planes. Now as I rotate this around, we can actually go ahead and see that that intersection on that line is still occurring. So I thought that that was interesting. Now it's not going to change the slope of the line, but it definitely has a different concept of planar intersection. I'm sure that this could occur in multiple other ways as well. It would be, similar to that style that we see here. It just would be maybe going through some other octants, but it would be still intersecting that line. So now what we're going to do is we're going to jump into slope. And I want to just reference my actual written part of my answer here. I think slope in this case can be looked at from a 2-space version and a 3-space version. So that's what I first mentioned. And in 2-space, what I did is, because we can see that the z-value is 0, I went ahead and just knocked the z-value out completely to make it a pure 2-space example. And I solved for slope just using the normal formula. And I found that My ultimate change in y over my ultimate change in x was 0 over 3, which reduces down to 0. 0 divided by any number is a value of 0. I then took this to 3 space, and in 3 space, we can determine the slope in respect to the z-axis as our rise, and then in the respect to the xy plane, which will determine our run. So in order to do this correctly, we actually have to go back to GeoGebra. So I'm going to go to this example. And when we're looking at the z, there are no z values. So therefore, the rise will still be 0 here. The run is going to be looked at a little differently, and I think the best way to look at this is actually if I just turn it this way, and it almost becomes completely 2 space right now. It's like a bird's eye view. And what we're doing here is we're literally just counting. Any horizontal or vertical line can have that countable ability because you can associate the idea of a number line with the distance. So here what we're seeing is that we are going to be 3 units between A and B. So that would be a 3-unit run. So I'm going to go back and switch to my problem here. And so again, the rise with respect to z would be 0, and the run with respect to the xy plane would be a countable distance of 3 units. If we go ahead and reduce this down, 0 divided by 3 is again 0. So in both aspects of 2 space and 3 space, we're getting that the slope is going to be 0. So again, this was for task number 3 in week 7.